His name is Josef Widder. I hope that I pronounced that right. Joseph is a principal scientist at Informal Systems. He started to work on Cosmos in 2019 with a focus on fault-tolerant distributed protocols. He contributes to design, formal specification, and automated verification of these protocols. Now, before joining Cosmos, Joseph was active in academic research, co-authoring more than 50 academic papers on the theory of distributed algorithms and on new methods for verifying fault-tolerant distributed algorithms by model checking. So he's with us today, Joseph. I invite you up onto the stage now. He will be talking to us about building bridges, exploring the design space for connecting blockchains, and of course, as we move more and more into the interoperable blockchain world, this topic is highly fascinating and highly relevant. So, Joseph, I look forward to your talk. Please take it away, and I will take myself off the stage.
Thanks a lot for the introduction. Thanks. Well, my talk is about building bridges. We're looking into bridges recently, and I'm going to talk a little bit about what we've learned in the recent months. So, for those who don't know, Informal Systems is a company that was sort of the main idea of verifiable distributed systems and verifiable organizations. The interesting thing here is really verifiable, and this is also the core of things that interest me. So I'm really interested in while I like new features being brought to the ecosystem, I also like figuring out whether they actually work and what it means that they work. So the core for us really is to make sure that the things we're building are working. Since blockchains and the bridges between them are going to be a very important infrastructure in the future, we should rely on them. We should be able to rely on them for this part of verification is important. The talk is about bridges. So the point really is that our view about the future is not that it's going to be one blockchain, but there are many blockchains, one for each application, and since you need to communicate from time to time, there is different ways of bridging between the chains and getting information across. And this is sort of the high level area I'm talking about today. So in particular, I would like to tell you a little bit about the experiences that we had in the last year, a little bit more in the year, partly from working also on audit. So we did some review of some other projects, and for instance, we looked at Lightbased, which is a general purpose protocol, which has been understood as the TCP/IP of blockchain. And also we looked at Interlace inter-PPC, which is a Bitcoin protocol bridge, which the designs are slightly different. One is because the IBC is Lightbased, also because you have the opportunity in IBC to run smart contracts in both ends of the bridge. Well, you cannot do that on Bitcoin, you need some other way around it, and the solution there was incentivized option type. Yeah, so we've found both designs robust. They address the adversarial environment they run in, which means trust no one and verify all. But still, I would like to share some insights and give some pointers on what we should consider important in this kind of designs. So I'll like to start a bit by talking of how to specify. So what does it mean, what the bridge is supposed to do? Then I'll talk a little bit about ways to build bridges, how we are going to check that what you build is actually what you're supposed to build. And I'll wrap up with some lessons learned. That's the plan for today's talk. So just to be clear, a bridge, there is a connection between two chains. And there are multiple components. Typically, you have two chains, A and B, and a contract on them. And then you have some off-chain component, which is the active component in this architecture. So the interesting thing is that typically in distributed systems, we have active participants talking to each other. So if you think about, consensus in the blockchain, you have validators that exchange messages, they are active, they receive messages. In some sense, chains are passive. right? They receive transactions and they store transactions, but they're not actually acting from a conceptual viewpoint. If you want to get information from a chain A to a chain B, you need someone in between who is actually, reading some information on chain A and trying to get it on chain B. So this from a viewpoint of a design space for distributed system, that's actually quite new and non-standard and also quite interesting. So yeah, I'll come back to typical one way to do this is to have light clients. So you have sort of a small version of the green chain stored on the red chain and vice versa. And you use these small versions to verify the information that you have received, but I'm coming back to that. So the interesting thing is that intuitively, it's super easy what most of the bridges are doing. So you want to send a coin from chain A to chain B. The interesting stuff here is really to say, well, what precisely does this mean, right? So if I would like to formalize part of this sort of being able to send and not having so spurious sends and things like this, I would start to write something like this. It should always be the case that the following holds: the value of the sum of currency A locked on blockchain A should be equal to the value of the sum in the currency B minted on B, something like this, right? And this intuitively just means that whatever has been sent on A should have been minted on B. That's a very intuitive way of doing that. But the point is, first of all, what does always mean, right? That's already something which is not so clear. If something just has been put on, there was a send event on chain A, for example, this perhaps hasn't reached chain B yet, right? So we are in this meaning of in-flight operations. The question also here, I'm a little bit shady about the value and sums and things like this. Therefore, also I'm not sure what the equality means. So there are, so the intuition is quite clear. So what it precisely means at all the time is something which is actually not so obvious to write. But this is then also the main challenge is if we should ask ourselves whether the implementation is correct. We really have to understand what is meant by correct. And here I've listed some of the problems with this definition, or how to satisfy this definition. So one, for example, that the locking on chain A and the minting on chain B are not atomic. There are events on two autonomous chains. So there are a couple of issues with that, right? If the locking and the minting are not happening at the same time, they open a time window in which these operations are happening. And then the question really is, when should this equality hold? Should it hold at the beginning of the transaction, at the end, somewhere in between? You have this problem of this in-flight information, transactions that are currently relayed from chain A to chain B. So it's not really just about the information on the chain, it's also something that's going on in between. And typically we also, or often, sometimes we see this kind of race conditions. So for example, if you, we might believe on chain A that the action on chain B has timed out, and therefore we're going to take some rollback action, for example. But the point is, what happens if I only believe that the timeout happened, but actually it didn't happen? So we are in this unclear situation. So all these scenarios that can happen, or that happen in this architecture setting. Between the components, the two chains and the relay in between, make this definition of the equality already not so clear. The other thing is typically you have some incentivization there. You have some punishment for certain participants in the protocol, and they are often taken from the same account, from the same money that is locked. But then also this, when you think about the equality and some punishment handling, these definitions are not so clear. So it's hard to define these things, but still if you want to talk about, correctness and what the thing is supposed to do, it's super important to do that. So the thing that we learned in these audits, for example, that often we are asked, look, we are concerned about concurrency. There's some concurrency on this component. Can you check whether the concurrency breaks the system? And often the answer we have to give is, it's not, I don't know, because I don't know what it means to break the system, because I don't know what the system is supposed to do. So therefore, it would be good always to have this sort of properties that describe what the bridge is doing, and it's not describing how the bridge is doing it. So things like you can just, for every function that's executed on a chain, you can define pre and post condition, and post condition could be that the new sum is the old sum plus the amount. So this doesn't describe a program, this just describes a transition of a function basically. Or you have some invariance over the contracts, so that the sum should always be smaller than something, right? Or you have some invariance that constructs states of two contracts. So that's already much more interesting, right? Because here in the first two points here, I talk about properties of the sort of one chain, of contract on one chain. But here I talk about invariance on two chains, and these are already typically much harder to formalize and to get right. But if you think about the correctness of your system, this should be done. And there are other properties, of course, system properties like, for every event X on chain A, there will eventually be an event Y on B, right? So if you think about sending, this would typically say, okay, for every sending event on chain A, there should be a reception event on chain B. And these are temporal properties, and they're also typically between two chains. So it's very important to specify these, so to have design documents that go together with the code that explain on a higher level what this thing is supposed to do. So having sort of the goal in mind, and if we're able to describe what the system is supposed to do, there are different ways to build bridges. And I'll want to give a little bit of overview here about the things that we have found. So the interesting thing is the easiest thing for implementing a bridge is something like this here, right? Hi, my name is Mike. I'm a bridge. If you send me one Bitcoin, I'll send you one token on your favorite chain. Of course, what can go wrong with that? And the point is somewhat obvious, right? I don't know Mike, so I've seen there was a Mike in the channel before. It's not this Mike who is talking here, but of course there's a matter of trust. And the technical challenge that we have in building this system is that we want to minimize the trust that you need in the system. And when I say trust, it's not only in trust of that I believe that Mike is a good person and it's a person who is doing good. It's also the trust that I have is that Mike is running a bug-free software, right? Question is, can I shield myself from bugs running on components I'm not controlling? So if you think about, again, the token transfer example and what can go wrong, there are so many things, right? You can just, the token never arrive. The token may arrive later than they should. Just half a token arrives, although one token should arrive. This half token may arrive late. Too many tokens may arrive, right? So it might also be that, Mike running a buggy software, and therefore Mike is going to incur the cost of running the buggy software. It might also be a scenario. So this sort of says that all of the involved parties are sort of characterized by a couple of points here, right? They have the incentive to misbehave because there is financial benefits on the line. They potentially run buggy software, and they might also be hit by a physical event, by being disconnected from the network, or by some, I don't know, a hit of a particle or something. So all these things, if you want to think about, I'm going to implement this property of sending the coin from chain A to chain B, is something that plays against you and that you have to counterbalance. So, and what is well understood also from my academic past, but also from the industrial experience I've gained, is that designing and implementing distributed systems is hard. They are super complicated. There are many components running in parallel. And the interesting thing about the bridge is that it's a distributed system that is made out of distributed systems. So this is really a hard problem that we want to address here. So there are a couple of design patterns that we observed in the ecosystems. So one is typically based on off-chain components or Oracle. So you have someone like Mike who's just offering his service to get information from chain A to chain B. Sometimes Mike is replaced by several persons, like a quorum of or a set of participants, and you have to do some threshold signatures, things like that. Or there are these solutions based on light clients. So you can use cryptographic verification there, and so that you are not relying directly on these off-chain components. So the things that you have to keep in mind here, if you want to design this, is that really you have to think about how do if you design a protocol, how do you shield against Mike lying to you? So typically you put in financial incentives and punishment there. So even if it's just one, right? There's if you design a protocol, there's some complication already to that. You can go for a sort of decentralized solution, right? In addition to Mike, you also could have an Alex and chain. And this actually is not one, it's not a central point now, but you have like 2 out of 3. I wouldn't call that super decentralized. You can think of Alex and chain being partners. So perhaps they have the incentive to work all the time together. So it's not so decentralized as it might look at the first sight. And of course, you can sort of pump up this scheme to have like hundreds of different entities running off-chain software, and you put some majority votes, or you do some 2/3 votes to decide what actually is going to go from chain A to chain B. This typically gives simpler designs, right? If you just have this centralized solution with one with Mike sending information around, it's much simpler, but it's super hard to get the incentives right. So we actually need to come up with an economic model. The problem that you have to deal with is, first, you need someone to do it, right? You need someone who actually is interested in getting information from chain A to chain B, which might not be that obvious why they should do it. At the same time, you need them not to do bad stuff. You need to punish them if they try to run away with the funds. You're dealing with external, fluctuations in exchange rate, which means some instability in the environment. What someone believes is the rational behavior. If there is, for example, stable exchange rate, might change substantially if there is a sudden drop in one of the currency's values. So here, really, the getting the incentives right is super hard, and this is sort of the main challenge here. The second solution that is out there is light client based. So rather than having a lot of logic on the relayers here, most of the logic is on the contract, and the funds are controlled by the contract and not by some off-chain component that signs transaction. And you're going to put you verify against the light clients. So you have cryptographic proofs. But basically, you are going to submit actually the payload, the data to the contract, and you're going to submit the proof or the Merkle root to the light client component, and then it's able actually to verify, to check what happens, whether a transaction happened on chain A, and use it in the state transition of chain B. There are a couple of as always, there are pros of cons, and the interesting thing is that the incentives are much easier in my understanding. You just have to get someone to regularly perform updates, which is somewhat simpler than thinking about all these fluctuations and everything. And you actually don't need incentives for lying. You're relying on the correctness of the cryptographic verification, so the relayer cannot break the signatures. So they are just there to ensure liveness, but not to ensure safety. This also means that the bug in the relayer is typically not safety critical, right? If you think about this solution with Mike, and instead of, because there's a bug, instead of sending a transaction of 1 token, it sends a transaction of 3 tokens. This breaks an invariant of the system because it might be just a bug in the software. Here, you don't have this kind of behaviors. So you shield yourself against that. So this also means that the safety is largely inherited from the chain safety. So from the guarantees, from the other side's guarantees of the chain, you get this. And finally, which is quite interesting, also properties that all the proof of what happened, you have the trace of the transactions on the chain stored, and nothing is sort of left in the on off-chain software. Of course, the cons, it's more expensive. And the other thing, which is the challenging part, is that the on-chain light guides are not automatically as reliable as the chains they observe. So I'll try to give a small example about Tendermint and Cosmos. I see that I'm a little bit short in time, so we'll keep it short here. So here's a nice drawing. Basically, you have a Tendermint network with full nodes running consensus, and what you use for blockchain for inter-blockchain communication is light client logic, right? So someone who from time to time comes and wants to read the state, and typically you don't want to follow all the blocks on the remote chain. You're just, whenever something interesting to you happens, you want to have that. So there are some issues. What you're having here is basically you do a remote read from this chain here, and the problem you're facing with is that this reading only from time to time is less robust than running a node, right? So if you have your favorite blockchain whose blocks you follow, and you go to sleep and you come back 2 years later, and you haven't seen any information for 2 years, it's super hard to figure out what happened there. And if someone is trying to attack you, they had 2 years to come up with some alternative history, and it's super hard to prevent it. So there is these differences in on-chain security and off-chain security that you have to take care of in these designs. I wanted to go detail here, but since I'm short on time, I'm going to skip that. So what we are doing at Informal to figure out that you build what you're supposed to build. So what we are basically doing is protocol reconstruction analysis. As I said, writing these properties, what is formally happening is super hard. So we try to, and typically the artifacts we get are just software and typically write not very detailed documentation. So we try to understand what the protocol is doing. We try to understand what the protocol is supposed to do and try to capture some analysis and figure out whether some vulnerabilities on the protocol level. So this sort of addresses 2 things. One thing, we try to find flaws in the protocols, and also some discrepancies between the documentation and the implementation. So that's sort of the base analysis that we can do here. What we also do at Informal is we try to use formal methods. So we're building our in-house model checker. It's Appalache. It's based on TLA+. We have several methods in using it. So one very appealing one is adversarial testing, where we use to capture the central points of the protocols in the formal language TLA+ and generate test cases from that. And a little bit more automated, we also do model-based testing based on TLA+. That allows us really to derive deep test cases and code-specific test drivers. So the lessons learned, to wrap up the talk. So first of all, formalizing what the bridge is supposed to do is hard, but it's important. We talk about distributed systems, writing invariants is painful, I understand that. But for this kind of systems, it's super hard to be precise of what we're expecting from the system. And then, if you want to check whether what the implementation is doing is what it's supposed to do, it's also hard. But of course, it's impossible if you haven't done completed point 1. This is really something that we often observe in conversations. We ask someone, so what is the thing doing? And then we get an answer of how it's happening, in which sequence the function is called. So it's really important to just capture also what is done. Another thing, which is the big problem, or it's the problem both from the automation side, but also from the mental side of understanding the system, is that the code is not the whole story, right? There's code on chain A, code on chain B, there's off-chain code, and whether this thing is correct or not may not know, but just looking at the code, you might not figure out whether it's correct or not. It might depend on when, whether, and in what order functions and all these components are called. And that's quite challenging. The other thing is that there is no bridge which is 100% robust. So often there are implicit assumptions, and this should not be you shouldn't be afraid to make them explicit. Okay, it's just important to understand to everyone who uses it what are your assumptions, what you can expect when they hold, and what you can expect when they don't hold. So it's very important to make them clear, and I think it's also important to minimize them. So if you do not have to rely on the correctness of a specific piece of software for a specific property, then don't. And yeah, finally, bridges are infrastructure, and we are going to use them very heavily in the future. So we should be serious about the correctness. And yeah, don't design our Slack, which means do design documents, capture your decisions, capture your properties. This is what we learned in all these exercises. I'll stop here. Thanks a lot.
Awesome. Thank you so much for your talk. Like bridges are such critical infrastructure, and sometimes they may not be the sexiest, or maybe you might find it sexy, but like it's incredibly hard problems to face. And thank you for sharing your insights, and definitely many important lessons to keep in mind. And so that we don't design over Slack or anything like that. So thank you for your talk. We got some questions from the audience, if you have the time to take them.
Sure.
First question from Jonathan Lorimer, who has been an all-star with the questions the whole conference. He's got 4 upvotes for this question. Are there any solutions to the large cost that three-layer operators incur? Would chain foundations or validators or users bear the cost if external incentivization is the only answer?
Yeah, I think I have some echo here. So I think the question about the cost for the relayers is really, for me, the main point is what do we understand of a relayer? So I've explained here the relayer of an independent component, and I think your question also sort of indicates that the relayers incur the cost. The reality somehow is that if I want to get a transaction from chain A to chain B, somewhat I have the incentives to do the function of the relayer. So my feeling is that this is something that will become my responsibility, and then sort of this should be this kind of cost. I think we should deal with in the incentives of the protocol we build on top of that. So I think that really the point really we should understand is that the components that we see here in the architectures and the designs are not necessarily the same persons. It's not different persons just because they're different components. And that's something really for me to this is what I currently think about, but perhaps I don't have the complete answer yet. But yeah.
Awesome, thank you. Next question. Are there any good examples of trustless bridge designs that you are currently a big fan of?
Of course, I like IBC. So IBC is based on light client security. You don't. I mean, trustless. The question is, what do you mean by trustless? You still, if chain B is your favorite chain, you still have to trust chain A to be okay, and that the validators on chain A behave nicely, or a certain set of them, right? But at least what IBC is ensuring that you don't rely anything on off-chain software. There's nothing on if the off-chain software is super buggy and untested, still IBC doesn't break any invariants, and that's super important. I think really to have everything that trace on-chain, and I think this is a very good example there.
definitely a great example and seemingly leading the way in trustless bridge designs. So next question is, what is the biggest drawback of having blockchain over blockchains as a bridge?
I mean, one thing, so if I understand correctly, the idea is to have one centralized blockchain that sort of serves as a hub to follow through information between the chain, if I understand correctly. I guess the main drawback would be the latency, right? It involves transaction times of 3 chains. Advantage somehow is that the sort of what would be off-chain software is now on-chain again. Yeah, and of course the incentives, again, we are in the same sort of question whether this chain in between, what's the incentive there to actually do the business for chain A and chain B, I guess.
Cool, thank you. And last question here from Anonymous. Can game theory inform bridge design?
Definitely. I mean, that's the big point. Getting all these incentives right, it's super hard. So I think that in the designs that I've seen, they are all solid. I believe them, but I'm not a game theory expert. So this is something where really I think there will be a lot of research and work done in this area, and we're definitely going to do that also at Informal.
Nice, awesome. Thank you again for your talk. And yeah, like to me, it seems obvious that like yeah, game theory would inform bridge design because it's all about incentives, right? So
yeah, totally.
But yeah, thank you again for your time. Thank you for joining us. Where are you calling in from?
Thanks for having me. From Vienna, Austria.
Vienna. Okay, so it's like afternoon for you right now.
Exactly. Yeah.
Nice. Well then, thank you again for joining us today. Really appreciate you sharing your insights again on bridges. I think everyone appreciates it. So thank you. Feel free to stick around and hang out for the other talks. But yeah, we'll see you again soon.
Thank you. Bye-bye. Bye.
Bye.